basically, today we're going to be doing simulated annealing and constraint handling in optimization. So let's start with simulated annealing. So last time in the optimization session, aka optimization part 1, we did hill climbing and how to formulate an optimization problem. So because we're going off of the same aspects, can anyone remember what the 4 parts of formulating an optimization problem are? So I'll give you a clue. One of them was creating a valid objective function and saying whether you want to minimize or maximize it. What were the other 3 things you have to define when you're formulating an optimization problem? Yep, search space was one of them, correct. Candidate solution. Candidate solution is not quite one of them. Candidate solution was more like Victor's session on certification and NP and P. So yeah. So yeah, good try though. So yep, design variables, correct. Search space or state space, yep, and constraints, good, yep. So that's all of them. So the 4 things we need to specify when we're formulating an optimization problem is the objective function and whether we're maximizing or minimizing it. We need to specify the search space, which is the space with all the generated solutions that we want to search. So we'll look at, in constraint handling today, basically, we're going to look at how we can modify the search space rather than the constraints. So the search space will include all the candidate solutions that we generate. So anything in the search space will be a candidate solution. And then it's up to the constraints to help us decide which solutions are valid. So one thing that we can do later on, we'll see today, is with constraint handling, we can, instead of writing it as constraints, we can reduce the search space to only include valid solutions anyway. So then we don't generate invalid solutions, because that would be a kind of waste. Like, you generate a solution, it turns out to be invalid, that's a waste, right? So if you only generate the valid solutions, then you just have to worry about which one of the candidate solutions is optimal. You don't have to worry about, invalidating or validating some of the candidate solutions which you're trying to generate. So that's an optimization problem. Cool. So once you have formulated an optimization problem, you need to solve that optimization problem. You need to do the work that you formulated the problem for. So how do we, let's say, specify to an algorithm how to solve the optimization problem? So just like how we said we needed to define 4 things to an optimization problem in order for it to, be a valid optimization problem, what are the 4 things we need to define to the algorithm that's going to solve our optimization problem? There are 4 things that we need to define there as well. Whether that's hill climbing or simulated annealing or any of the variants of hill climbing, there are still 4 things that we need to specify to an optimization problem algorithm, like the one that solves the problem, in order to get it to work. So does anyone remember what these 4 key aspects of an optimization problem algorithm are? Define a heuristic. Yeah, so some informed searches would use, so heuristic could be one of them, but it's not like one of the 4 key ones I was looking for. I'll give you a hint. One of them is called the neighborhood operator, and that defines how you generate neighboring solutions of a current solution. So that's one of them. Does anyone remember the other 3 that we need to define for an optimization problem algorithm? If not, that's fine. I don't think I explicitly mentioned it in the last session. I'll just show you today. This is what I was talking about basically. So if you guys can see the screen here, these are the things that we need to mention. So as we said already for the optimization problem, the four things are design variable and search space, the objective function, and the constraints. And okay, my bad. Oh no, not my bad. It's still four things. Yeah. So for the algorithm, we need to define the algorithm operators, which include the representation, which means what kind of data type is the initialization procedure was one of them. Good job, Sid. So what kind of representation are we giving the variables basically? So variables inside the design, basically the design variables. So we have the optimization problem where we specify design variables, but into the algorithm, we need to specify an appropriate data type. So you know what, string, vector, integer, real number, float, boolean, whatever. So you need to specify that. And the representation should have some kind of like bearing with, you know, how we're initializing and how we're doing the neighborhood operator. It should make sense, right? So, for example, if we're trying to optimize a pathfinding algorithm, aka the shortest path, we would need to set the representation as a vector. And this vector would be the sequence of the paths, basically. It would contain all the different paths that we've visited in a certain solution to get to the goal node. So that would be the representation. Cool. The initialization procedure. So the initialization procedure that we need to specify to the algorithm is how we want it to start, kind of. So we wanted to just start at random points, like we do with gradient descent, and actually with all of them now that I think of it. So yeah, do you want to just start at random points? You can start with I don't know, a random point and then do gradient descent. You can start at a random point and do hill climbing. Start at a random point and do stimulated annealing. In fact, when you're doing unsupervised learning, you even start with centroids at all random locations. So that's normally like the initialization procedure. But however, it's not always like that. Sometimes you can use a heuristic or something like that, which is what Victor was saying. You can use a heuristic to kind of get a more of an informed learning kind of approach to saying where you want to start rather than just doing it randomly. And finally, the neighborhood operator. The neighborhood operator is like how you want to go up or down, or like how you want to generate the neighboring solutions to the current solution you're at. So cool, great, you've represented your design solutions, let's say. You've also initialized the problem space, right? So you've now chosen a random solution to start off at. Great, that's in the search space. How do you now choose the next ones to go to? How do you choose the ones that you have from this solution to compare and move on to next? Well, that is decided by the neighborhood operator. So you could say normally what it is every independent variable, every free parameter that you have to work with, you increase that or decrease it by, let's say, 0.1. And those would be two solutions. I remember we did this last time with an actual example of hill climbing. So I think Victor specified the neighborhood operator was 0.1. So then what we did to find the neighboring solutions was just increased x by 0.1 and decreased x by 0.1, and then compared which one gave us a higher value of the objective function because we were trying to maximize. And then we just moved to that solution. And that's how hill climbing would work. Well, the OG hill climbing anyway. Don't know about the variants. So that is the neighborhood operators. So is everyone clear, just as a recap from last time, what we need to specify in order to formulate an optimization problem and then use an algorithm to solve that optimization problem? There are four things to formulate it and three algorithm operators, I guess, to solve the problem using one of these algorithms. Everyone clear on what these are and why they are? Great, cool. That's what I like to hear. So now we can get on with simulated annealing. So what is simulated annealing? So it's an algorithm for optimization, just like hill climbing. So you need to specify things like the neighborhood operator and initialization, representation, etc. So this is an optimization algorithm which rarely gets stuck in a local optima and tends to basically converge on the global optima. That's its advantage compared to other ones, and that's why we tend to use it. So that's its point. It tends to not get stuck in local minima. It tends to always go to the global, and you'll see why later. So, and it uses a principle from physics known as the Boltzmann distribution for thermodynamics. So those of you thermodynamical about this, you'll be able to see how this is related to physics. So I don't know if any of you know what that is. Anyway, cool. So the first step is generate an initial candidate solution, aka initialization, which is what you would have specified by the neighborhood by the algorithm operator anyway. Then you generate neighbor solutions for this initial solutions, which you would have specified by the neighborhood operator. Then if the move improves the current solution, it's always accepted. No questions asked. If so, you say we're gonna assume like for the rest of this example, I'm gonna assume we're trying to maximize. If you're trying to minimize, it would be the same thing, but yeah, the other way around. So if we're trying to maximize, and let's say one of the neighbors improves the or increases the objective function, then it's always accepted. That's like non-negotiable. However, even if it doesn't increase the you know the solution, the objective function, it might still be accepted. It's not just like black and white in hill climbing, well, the OG hill climbing, where it's like accepting if it's better and non-accepting if it's worse. So it could accept it, but it has a probability to also not accept it. And this is the probability that's represented by the Boltzmann distribution, which we will look at later. Just to give you guys a bit of context, because I think it's kind of fascinating, is that simulated annealing comes from the engineering term for annealing, which is actually used in metallurgy, right? So that coins the term where like you heat up a metal to a really high temperature, and then you very, very, very gradually cool it down. And what this does is it aligns the particles, it aligns like the atoms and molecules inside the metallic structure to all, yeah, it aligns all of them up. And what this means is that when you gradually cool it down, because you are gradually cooling it down, which is the key bit here, you can't just cool it down straight away because that would actually harden it. Because you are gradually cooling it down, all of them particles remain aligned with each other, which actually makes the metal a lot more ductile, aka makes it a lot more easy to bend and twist and all of that, which can be useful for several purposes. So that is the process of annealing used in physics. What we're doing here is kind of like a simulated annealing. So we're simulating the same process, but instead of gradually cooling down a metal for it to become ductile, we are gradually cooling down a probability function to make it accept less worse solutions over time. And we'll look at that in just a sec. But anyway, that's the basically where the term simulated annealing comes from. So basically, this terminates when a minimum temperature is reached or the solution does not change in value. So yeah, as I mentioned over here, as different from hill climbing, simulated annealing does accept bad moves. But it accepts on a probability, as I said. So how do we decide which bad moves to accept with simulated annealing? Well, what do we want basically? We need to decide some kind of criteria, some kind of probability function that has a high probability at the beginning of yeah, basically like the explore stage we call this. So when the algorithm has a high probability of accepting any solution, no matter how bad it is, we call that the explore stage, which happens right at the very start of the algorithm. It pretty much just accepts every solution, no matter how bad or good it is. And then it's called the explore stage because we are going to every single solution of every single neighbor of a solution. We move to all the neighbors and we go off of those as well. So we're accepting all the solutions and therefore we're just exploring. We're trying to get to as far away from the initial as possible in different directions. So we have kind of a better understanding of the search space we've been given. We have a better understanding of the problem we're dealing with because we've explored the search space a little bit. However, Doing this continuously for a long time would lead to so many different paths. As you can imagine, like initial solution could have, I don't know, four neighbors. Then those neighbors would have another four neighbors, and those neighbors would have another four neighbors, and so on. And if we keep accepting all solutions, we'd eventually probably run out of memory, if I'm being honest. So once as time goes on, the temperature also decreases of the probability function, which is actually this function here. I just wanted to give that out so you guys might be able to see what I'm talking about. So the temperature decreases. Um, don't worry about the delta E. Just treat that like a constant value. But the temperature is super high to start off with. So you can see the temperature here would be near infinity at the start. So if the temperature is near infinity, because it's the denominator of the exponent, it would make the exponent tend to zero, because the denominator tends to infinity. Hope that makes sense. So it would be effectively tending to e to the zero. Does everyone remember what anything to the zero is? It's 1, right? So it would have a probability of 1 of accepting a bad solution, which means it will basically always accept a bad solution. And that's the explore phase. We accept every solution, and then we start filling up, we start exploring. But as time passes, similar to hill climbing, we exploit and eliminate. So that sounds kind of like, illegal, but yeah, we like exploiting and eliminating. So basically, this stage, temperature decreases gradually, but at one stage it will be quite low. And what this means is the exponent, this probability function, starts getting lower and lower because temperature is the denominator of the exponent. As temperature decreases, the exponent um, increases, right? Which would mean like it would go from e to the zero, which is what it started off as, to e to the 0.1, 0.2, 0.3, and so on. So the value of the probability would start. The value of the exponent would start increasing, and because it's beneath 1, um because it's beneath 1, um the probability would also start decreasing. So because the probability starts decreasing, that's when we exploit and eliminate. So we eliminate net bad solutions, and we exploit the fact that we explored at the start, because now we have a big hold over the search space. We have a lot of understanding of the search space. We have a lot of different neighbors everywhere. We have a lot of different visited nodes, etc. So we have a lot of space that we can now go off of, right? So now let's say we have because we had initial solution, 4 neighbors, visit those 4 neighbors, then another 4 neighbors for each of those neighbors, and so on and so on and so on. We could have hundreds of like solutions currently stored. And now all these hundreds each have 4 neighbors. So now from these hundreds of solutions, we can now choose the best ones, right? We can choose the good ones, and we can keep going like this until the temperature keeps decreasing and decreasing, and we only choose the best of the best, which leads us quite often to the global optimum, not just the local optimum, but the global optimum. And purely because we had the explore stage at the start, where we kind of explored a lot of the data set. Now, when we're only choosing the good ones, we have started in so many different positions. We are very, very, very likely to get to the global optimum. Does that kind of make sense? Does everyone understand, in theory, how this gets to the global optimum as opposed to hill climbing, which normally gets to a local optimum? Yeah. Okay. Victor saying yes. Great stuff. Thanks, Ollie. So okay. So what do we get? As I said before, the algorithm accepts worse moves with some probability less than 1. The probability decreases exponentially over time, because obviously t is an exponent, and the probability decreases as the temperature goes down. So this function here, that is the meat and potatoes of simulated annealing. This kind of if we get any question about simulated annealing in the exam, it would be about this function, pretty much. So P equals e to the delta E over t. That's inspired from thermodynamics, but represents the probability of accepting a bad move as the algorithm progresses. Where e to the delta e is equal to the e of the basically the kind of like an energy, like it's kind of like how good it is, not energy, but it's kind of like how good it is. X nu minus e to the x current is less than or equal to 0. So basically, yeah, that's what this is. It's kind of evaluating how good it is compared, how good is a neighbor compared to the current solution, and then T is the temperature, obviously. So that's how this function works. So the impact of the temperature. So what you might be thinking, what's temperature? The only reason it's called temperature is because we've copied this from. This is originally a thermodynamics equation. We've copied it into computer science, and we're simulating annealing. So that's why it's still called temperature. Boltzmann's concepts did not die. So the impact of temperature, to start off, T is set to a very high value, so which makes the probability more or less equal to 1, as I said at the start, because the exponent goes to 0. And then this is the key bit here that you probably need to remember, to be fair. It's an update schedule. That's how T is updated. So an update schedule is, or I don't know how you guys like to pronounce it, schedule perhaps. Update schedule is used to reduce it gradually, such that this basically t plus 1 is equal to alpha t to the t. So basically what this means is this is an iterative formula, and it basically is showing that to get to the next value of t, so I guess this should ideally be subscripted, I guess. Actually, no, it's a function. I can leave it. So to get to the next value of t, aka like what we're going to have in the next iteration, all we do is we take the current value of t and multiply it by alpha, which is a hyperparameter. It's like the learning rate, right? So alpha is a hyperparameter we need to pass to the algorithm in order for it to work. So like how we said, neighborhood operator, initialization process, and representation, with simulated annealing, we also need to pass this hyperparameter. But it's not a defining thing of the problem. So I guess it's not included as a general one because it's specific to simulated annealing. So you can think of it like the step size hyperparameter that we have in gradient descent. In fact, it uses in gradient descent, it's called learning rate. So in hill climbing, it could be, no, that's called neighborhood operator, right? But here's a unique one then, step size, right? Hyperparameter. And it's denoted by alpha, just like how learning rate is in gradient descent. If the temperature decreases slowly enough, um, what's the value of alpha going to look like? It's going to be, well, naturally it's going to be less than 1 because we want the temperature to decrease over time. So it's between 0 and 1, if that helps, I guess. You can have it as like 0.1, I guess. Probably you have something small, so the temperature decreases. However, you wouldn't have it too small, and we'll look at that just now. Sure, but is it 0.5 or 0.95? You could have it set to whatever you want, as long as it's less than 1. Simulated annealing would make sense. Um, you try to make it close to 1, to be fair, now that I think of it, because you want temperature to decrease gradually. The crucial aspect, very, very crucial aspect of simulated annealing, exactly, is that you want to gradually decrease the temperature. Annealing does not work if you suddenly decrease the temperature. In like metals, right? If you heat up a metal and you suddenly decrease the temperature, it actually hardens the metal because the particles like don't align. If you gradually decrease it, the particles will remain aligned. So similarly, we want to do that here. We want to gradually decrease the temperature. That's the whole point of annealing, right? So basically, and similarly, how it only works in physics if you gradually decrease it. It only works in simulated annealing in computing if you if you yeah if you gradually decrease the temperature as well, very, very gradually. Because, and I'll say the reason why, because it's actually quite important. So if the optimality of the algorithm. So later on, we'll look at the performance, right? This is only going to give you the global optimum, or like has a high chance of giving you the global optimum, if you decrease the temperature slowly enough. So yeah, that's a fair point from Ollie. So he's saying that he's just looked it up. The value of alpha, aka the step size, kind of to define how we're going to do the update schedule of temperature. That is always approximately equal to 1. So it could be 0.99, let's say. So that really goes to show how gradually, right? It like the temperature goes down. It's really gradually. Like we will get 99% of the temperature each time there's an iteration. So you will only lose 1% each time. And when you do this, that is what ensures you get to a global optimum rather than a local one. Um, as you can imagine, if you set it to like zero point 0.1, which means you would have lost 90% of the temperature with each iteration, we would pretty much be done by the first two iterations. Like the temperature would have already lost the vast majority of its value. And yeah, would have not explored that much. The whole point of keeping the step size almost equal to 1 is that you want to gradually decrease the temperature because you want to have that explore stage. That initial stage where you're exploring, you're getting all the neighbors of every solution, whether they're good or bad, doesn't matter. That is where that explore stage is critical, as I mentioned before, to finding the global optimum. It's what separates this from other algorithms like hill climbing, and that only works if the value of temperature goes down very slowly, and that only occurs if the value of alpha, aka the step size, is near 1. Does that make sense for everyone? The gradual decreasing and how we um, set that in the update schedule. Good, cool. So now, as we have done with all of them, let's look at the performance of simulated annealing. So in terms of performance, we look at completeness, optimality, time complexity, and space complexity, as we have done for all of the algorithms we've looked at so far. So in terms of completeness, it's not complete, unfortunately. Yeah, I know, bummer. You thought it was a great algorithm. You thought like you couldn't go wrong with this one, but yeah, it's not complete. Meaning it's unreliable because um, this means that it's very prone to problems with your formulation. So yeah, if your if your formulation of the problem is valid and good and yeah, so you've defined all of the key things like the objective function well, you've defined the design variable, search space, constraints, you've designed all of those well, it could be complete. Your algorithm could be complete. However, if you haven't, then your algorithm is not going to be complete. So meaning, even if there is a valid solution, like a global optimum that exists, it won't find it. It won't find that solution, and that's what incomplete would mean. So yeah, it's very sensitive and dependent on the formulation of the optimization problem, which is what you have to do. So make sure you do that well. Okay, next thing, optimality. So simulated annealing is not optimal as it depends on the termination criteria and the schedule. So that schedule, I mean like the temperature schedule. As I said before, the temperature needs to very gradually decrease, otherwise it's not going to lead to an optimal solution. Time complexity, well, lucky for you guys, you don't have to memorize any time complexity here because there isn't one. It all depends on the temperature schedule and the termination criteria and a lot of things in the optimization problem. And same thing with the space complexity. It just depends on how you formulated the problem. So as you can see, simulated annealing is really good. It always it has a high chance of getting to a global optimum. However, it's only as good as the formulation of the optimization problem that you give it. If you give it a well formulated problem, it will smash it. It will give you the global optimum, no questions asked, really low time complexity and all that. But if you don't, well, yeah, it's gonna mess up. It's not gonna give you much good. So that's one of its drawbacks. Is really formulation. It's really sensitive to a bad formulated problem. Okay, pros and cons. When would you use it? When would you not? So simulated annealing can usually find a optimal or near optimal solution in a reasonable amount of time. Again, providing that the formulation is good, and it avoids getting stuck in poor local maxima by combining exploration and exploitation. So if, as we said, we have many searches, so we explore first, we have many solutions that we're concurrently working with at any given point at the end of exploration stage. And that means that even if, like, let's say out of the 200 solutions that we've already generated and we're currently using, even if 100 of them get stuck in a local optima or like a poor plateau or something, we still have like another half, like another 100 solutions, all generating neighbors and stuff we're still looking at that isn't stuck in a plateau. And that's why it's so good at finding the global optimum. However, the cons are it's not complete nor optimal. That it can't be if your optimization problem isn't good, and therefore it's not reliable. You can't always use it guaranteed completion. And the time space complexity is problem. So and problem and representation dependent. So again, that's very dependent on the problem. So basically, if you're catching the drift, basically the drift is that it's very good. It's good at finding the optimal blah 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 blah. However, it's very sensitive to a bad formulated problem. So if you formulate your problem bad, you're screwed basically. Okay, cool. Let's move on to next topic. So constraint handling. So we've moved on from simulated annealing now. So that was the last algorithm we needed to look at. So now we're going to look at how can we handle our constraints basically, so that we, uh, so that we, Victor, was that a sad face from now? Or oh, that was from before. Okay, cool. Never mind. Okay, so we're formulating our problems and how can we deal with the constraints, kind of basically, so we can help the algorithm out. This is about changing the constraints or handling the constraints, changing the formulation in order to help the algorithm. We're not trying to change the algorithm here. We're trying to change the formulation to help the algorithm. So basically, in optimization problems, constraints define the feasible region of the search space. So the search space is any solution that can be generated, and the feasible region is any generated solution that passes the constraints or is valid, basically. So constraint handling methods are used to ensure that the optimization algorithm can effectively search the feasible region and avoid or penalize infeasible solutions by modifying either the algorithm operator or operators, because we have a lot of them, or the objective function. So there are two things here. We can either modify the algorithm operators of the algorithm here, or we can modify the objective function from the initial problem. And by doing these, we can make it easier to solve the optimization problem basically. So the first method we're going to look at is modifying the algorithm operators. So how can we modify these algorithm operators in order to, you know, make our solving of the problem more efficient? So this involves modifying the search operators to generate only feasible solutions that satisfy the constraints. The algorithm operator is a function that generates a new candidate solution based on the current solution and can be manipulated to only generate solutions in a certain line. So basically this is like the neighborhood operator, I guess you can think of it. Like it's not exactly, it's there's some minor things that make it different, but in terms of simplicity, it can be, you can think of it like the neighborhood operator. How are we generating the neighboring solutions? Well, we could just generate them by like a plus or minus x value, go 1x up, 1x down, see which one's better. However, we can also put some like constraints kind of inside the neighborhood. So you can say go 1x up only if it falls on this line or something like that. Which is why an easier way I like to think about it is, instead of modifying the algorithm operator, you just modify the search space, which is effectively what we're doing here. The algorithm operator is a function that generates a new candidate solution based on the current solution. So we want to generate solutions that are going to be valid, basically. We want to avoid generating invalid solutions. We want to avoid generating a solution just for the constraints to tell us, actually, you can't have that one. So how we do that is by basically modifying the search space. So we only, because solutions are only generated in the search space, if we modify the search space, we can um, you know, avoid generating infeasible solutions. So here is one. I've given you some before and after pics here. So the before pic shows us the search space being R squared. So that's a set of, real number Cartesian product real number, basically, not like square numbers, just clearing that up. Um, which is basically coordinates, right? You have a set of two real numbers inside a set, which is a coordinate kind of, because we're looking at a Cartesian plane here. So the objective function was to minimize. Oh, I didn't tell you what the problem is. So it's kind of said at the top. Okay, so this problem is basically the classic Leonardo problem of finding a point on this line that's closest to the origin. So this is the objective function. We're trying to minimize the Euclidean distance from any point to the origin. The constraints being um, has to lie on the line y equals 2x minus 4. That's the only constraint. And we're searching the entire search space. So in this problem, this formulation, the issue is that we can generate a solution on any point of the Cartesian plane. The only search space we've been given is r squared, which is basically any point on the Cartesian point. As long as the two numbers, x coordinate and the y coordinate, are real numbers, it's valid on the search space. So we could have a solution generated here, 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 everywhere. And as you can imagine, most of the search space is not on this line. So it's highly inefficient because we are now generating solutions everywhere, and most of them are being told no, they're infeasible. Whereas we only want solutions on this line. So if we could find a way of only generating solutions that are on this line, and then all we'd have to do would determine which one's optimal, that would save us a lot of, generating unnecessary wrong solutions, which aren't going to pass anyway. So only if there was a way, well, there is a way, believe it or not. So the way is to basically do modifying the algorithm operator. So we change the search space here. So if you look at the after pick now, so the search space has changed and the constraints are gone. We don't need constraints anymore because every solution we generate is feasible. It's amazing. So basically here, the search space, xy defined by y equals 2x minus 4. So if that's our search space now. So we only generate values of x where, the y value would then, or we only generate coordinates whether it matches this equation, it falls into this equation. And this forces the algorithm operator function, which generates the new solutions, to only generate valid solutions. So we're never generating an infeasible solution. So that's not only saving us the computation time of generating bad solutions, but it's also saving us the computation time of going through each solution and seeing if it passes the constraints, because we've removed any possibility for it to generate an infeasible solution, meaning it only generates feasible ones, which means we can remove any constraints because we don't need them anymore. It's only generating feasible solutions. So we're actually saving computation on two aspects here. We're saving it on generating unnecessary solutions, and we're also saving it on checking each solution is valid. So it's very much more optimal. So do you guys see how constraint handling here with the method of modifying the algorithm operator has increased the efficiency of, the optimization algorithm? Is that clear? And does that all make sense how that works and why we're doing it? So you modify the search space so you don't need constraints. Exactly. Well, that's not always the case. In this case, we could do that. So that's the ideal case, right? Might not always be possible, but the idea is you want to limit the search space as much as you can so you don't generate infeasible solutions. That's the goal, right? If you look at here in the definition here, I've put inside this part, modifying the search operators to generate only feasible solutions that satisfy the constraints. So that is it in the ideal world. You can modify the algorithm operators for a problem so that it only generates the feasible ones, thus eliminating constraints altogether. However, sometimes it's not always possible to, define a search space like that, depending on the problem you're trying to do. In which case, you would still constrict the search space as much as you can, but you also might have constraints remaining. Either way, it's a lot better for the algorithm because there's less computation involved. But yeah, it might not always be removing constraints altogether. You could still have some. Does that answer your question? Okay, cool. Anyone else has any questions about kind of what constraint handling is and what how this method of constraint handling achieves the purpose of making it more efficient? I'm not seeing anyone typing in the chat, so I'm going to assume that we get this. Cool. All right, so let's look at the pros and cons. So this, remember, there are two methods. So you can modify algorithm operators or you can modify the objective function. We're about to move on to the objective function, but just before we do, we need to look at the pros and cons of the modifying algorithm operators. So the pros being infeasible candidate solutions will not be generated, as I've been saying this entire time, and it makes hill climbing and simulated annealing both complete. You didn't realize that one, did you? So we said before simulated annealing was incomplete, and we said before that hill climbing in the last session was incomplete. But we also said that it's dependent on the formulation of the problem. If you go back to this, it says not guaranteed to be complete. Where is it? Here. Simulated annealing is not complete as it depends on the problem formulation and design of the algorithm. So it depends on that. And this is exactly how you get it to be complete. You get it to be complete by, making the search space, by trying to eliminate the concept of infeasible solutions. It can make it both like reasonably and practically complete. So that is the big advantage of modifying the algorithm operators. It will make all these algorithms complete. And then may be difficult to design. Yep. So problem dependent. So Victor asked before, can we just do this where we remove all the constraints and always just have it in the search space instead? The answer was no, because it's not applicable to every single problem, especially more complex problems. You sometimes still need the constraints. And that's what this con highlights here. It's difficult to design and maybe problem dependent. So you won't be able to do it in every case. So you won't be able to make a simulated annealing and hill climb complete in every case because you can't do this in every case. That's the idea basically why it's incomplete. Can restrict the search space too much, making it harder to find the optimal solution. Well, it won't be valid in this case here because we're generating all the feasible solutions. But in some cases, if you constrict the feasible search space too much, it could lead to you only finding the local optimum within that search space. Say there's a problem where you could have optimals at any place, but you also have a lot of infeasible solutions scattered around this like optimal range. And then there's a section in between where it's like purely optimal solutions. So you could have the global optimum in that space where there's a mix of infeasible and feasible solutions. However, if you don't search that region, because that's not in your search space, your region search space region is like only the one where it's purely feasible solutions. It could lead to you missing out on a lot of good solutions, a lot of optimal solutions. It could lead you to missing out. So you don't want to constrain the search space too much, essentially, because that could lead to being counterproductive. You won't search everything. So that is modifying the algorithm operators for constraint handling done. We're going to move on to the second technique now, which is modifying the objective function. So there are two approaches for this, actually. It's called death penalty and levels of infeasibility. So this involves, let's just look at what modifying the objective function as a constraint handling mechanism entails. So this involves incorporating the constraint into the objective function, often by adding a penalty term for constraint violation, which is what we'll look at. So you can add a penalty if it violates a constraint in the objective function itself. So if we're trying to, let's say, minimize, we can, add a penalty to the objective function if it's infeasible, which would mean it's obviously not going to be the best solution because it's got a massive amount added to it. This means that the objective function, if we're minimizing, would be increased if a constraint is violated. Cool. So let's look at a prime example of that called the death penalty approach. So what death penalty does, it's kind of like sentencing certain solutions that have been generated to death. So in optimization problems, we often need to avoid infeasible solutions, like avoid generating them in the first place. And this is done by modifying the objective function. So the objective function is modified as the minimum. We want to minimize, basically, saying we're wanting to minimize, not the minimum, okay? We want to minimize f of x plus q of x. So f of x was the original objective function that you had all along, and q of x is defined as 0 if x is feasible, because we're trying to minimize. We don't want to add anything if x is feasible. So that would be 0. It would just become f of x. However, now here's the death penalty. If if the current value that we're at is infeasible according to the constraints, then we had a death penalty basically. So um, c otherwise c is basically a large positive constant, right? And this ensures infeasible solutions are worse than feasible solutions because you add a huge amount. The objective function goes way up. So it obviously can't be it can't be close to the minimum solution. It's a very bad solution. And that's what death penalty does basically. However, as you may have guessed, I didn't say the constant changes. It's always the same large positive constant no matter what the infeasible solution is, and that is what leads us on to the weakness. So the weakness of this approach is that all infeasible solutions have the same penalty. And this can make it difficult for algorithms to find feasible solutions in regions of the state space which are dominated by infeasible solutions. So um, say, as I said, there's a okay. What if you wanted to maximize? Yeah, so c would be negative in that case, or yeah, you'd be subtracting q of x from the original. Yep. So you just do it the other way around. Does that make sense? Great stuff. Okay. So that's the weakness because we're only using one large positive constant, no matter how infeasible it is. So I'm going to start using this term now called how infeasible. It's not a technical term, as you may have guessed, but I feel like it helps us visualize what's going on the most. So there are obviously naturally going to be some solutions which are very, very infeasible, like completely off the charts infeasible. And there are going to be some solutions which are like, really close to the feasible range. It could almost be feasible because of the way we written the constraint. Perhaps instead of like writing a less than in the perhaps instead of writing a less than or equals to in the constraint, we wrote a less than, and therefore solutions equal to that won't be within the feasible region. But the ones that equal to that would be way less infeasible than the ones which are like wildly off. So does everyone understand what I mean by more infeasible and less infeasible? Yes. Okay. Cool. But don't write that in the exam because it's not a technical term, and I'm not going to be held liable, and I don't take any responsibility for the question in that. Okay. Cool. Great stuff. Okay. So that's the weakness of this, which actually gets us onto our second approach. Levels of infeasibility. And this does exactly what you think it would. It solves that problem of the weakness before, of the every infeasible being solution being treated the same, right? This solves that problem. So not every infeasible solution would have the same massive constant added to it. So in this approach, we distinguish the objective value of infeasible solutions to help the algorithm find a feasible solution. So not every infeasible solution is treated the same. The objective function still gets a constant added to it though. So we still have f of x plus q of x if we're minimizing, where f of x is the initial objective function and q is the penalty term. Q of x is the penalty term. However, we have a very complicated q of x mechanism here. So it's not just q of x equals to c. We have a bunch of different constants, which is tied in with the constraints. So let's just look at this for a minute. So here, sorry, um, v subscript g1 is 1 if the corresponding constraint if the corresponding constraint is violated, and 0 otherwise. So this thing here, this is 1 if the constraint is violated, and 0 if the constraint is not violated. So what that means is we include this term basically if the constraint is violated, which means we want to add to this constant. We want to make the constant bigger because it's violated a constraint. Sorry. Uh, then um, if the constraint has not been violated. So if it is feasible, then we don't wanna like penalize the objective function for it for this specific constraint anyway. So we make this zero, and that basically like gets rid of this term because it's multiplied by zero. So and the same is done for all of these. So how many ever constraints you had? So in very complex problems, you'd have a lot of constraints, right? So you'd have a lot of values for q of x. So whichever constraints are violated, you'd put a certain penalty amount and add it to the value of q. And if it's not been violated, you don't add it to the value of q because you don't want to penalize it for something it hasn't done. So that's how this works basically. So this means that the more constraints and the more serious the constraints are that the solution has violated, the more the value of q of x will be. So it's not just one large constant like the death penalty. This differentiates between the infeasibleness. So if it violates just one, it won't be at that infeasible. Like the value of the objective function won't be increased as much if it's only violated one constraint. However, if it's violated two or violated all of the constraints, you'd have a very large value of q, which would naturally mean that it's not going to be a good solution because we're trying to minimize it. Ollie says, are G subscript I just constraints with an inequality greater than or equal to zero and h of j where they must be equal to zero? So you're asking like kind of like the differences. What are they? What is G? Okay, so these are functions that um tell us what constraint we're trying to give. So it's uh I think I might be wrong, so don't quote me on this, but I think how it works is um CG1 of x gets you the penalty term for a constraint. So I'm assuming G1 would be one of the constraints and G2 blah 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 would be constraints. Um and the C added to the front just means we're not doing that constraint. We're not looking at the constraint. We're kind of adding like the penalty term for that constraint. So because we don't want to have just the constraint. We want to add on the penalty term because adding on a constraint would be kind of meaningless. So we want to add a penalty term on for the constraint. So C is a constant, which kind of represents how important a specific constraint is. So if this constraint was violated, um, then if this constraint was super important, we could multiply it by a big value. So it would contribute a lot to the value of q of x. Whereas if this constraint was violated, but it's not too important if it gets violated, then the value of c here could be small and it wouldn't add too much to q of x. In terms of the differentiating between the g functions and the h functions, I initially thought they were to do with the real costs, real constraints, and heuristics, but I'm not too sure how that would work out. Feel free to um, correct me if I'm wrong, though. I'm not too sure. But basically, you can treat these as like constraints that would all be summed up in one massive summation to get q of x. The differentiating between what each constraint means, I don't think it's particularly required, but it would be good to know. So I'd be very glad to like have any suggestions, or if anyone knows what the difference between the g function and the h function is, pop it in the chat. So we say that g of I is a constraint that must be less than or equal to zero. Okay, so Ollie's saying that the g functions is a constraint that must be less than or equal to zero, and if not, we add c multiplied by how much the you're just saying what I was saying and questioning. Okay, yeah, so that's what I think basically. So that's what I was saying. So um this is the constraint, and then c is like you're multiplying it by how much you kind of how important this constraint is to like not be violated, if that makes sense. And that it's kind of like a mechanism of feature scaling, you could almost think. So you're kind of scaling each constraint based on how important it is to be followed. Anyways, it's not too important. I don't think we'll be asked specifically about this in levels of infeasibility, like what the different H or G is. But don't come at me if they do, because I'm not the examiner. I don't know what they're gonna put. Squaring the values of the constraints in the penalty term can make the distinction between the objective function and objective values even larger, distinguishing different infeasible solutions more effectively. Sometimes you square them. That's all that's saying. Yeah. Not only does that remove negatives, but if you square them, we obviously get with bigger solutions normally, unless we're truly dealing with numbers less than one. Um, so if we square them, we get a bigger span of solutions, and that would mean that we can more effectively distinguish, and minor differences in the constraint would make a much more bigger difference in the q of x if we've squared all of them, which can be good or bad. But that's just one of the techniques that's sometimes used. So sometimes you'll see that it's CGI of x all squared. Here they've used mod bars instead, but sometimes they square it as well. Anyway, so the pros of modifying the objective function, which is so this is not the pros of levels of infeasibility, by the way. This is the pros of the modifying the objective function as a whole, which includes death penalty and levels of infeasibility. So the pros are compared to modifying the algorithm operators. So it's easier to design. The cons are the algorithms have to search for infeasible solutions to design rather than just having to search the space only containing infeasible solutions. So yes, that is a point here. So we're still actually going to generate some infeasible solutions, but they'd just be like disregarded straight away because they'd have a really large um, objective function if we're trying to minimize. So in the case of this, um, we're still generating the infeasible solution. However, it would just remain a neighbor. It won't be the solution we move on to. So, unlike algorithm operator, where we modify the search space, when we modify the search space, what that means is, oh, has the recording ended? Hang on, let me just check. We are at 57 minutes. Okay, I'm just gonna. Okay, yeah, we're recording again. Great. So let's go back. Okay, um, so what was I saying? So the cons are, so you remember with the algorithm operators, we only generated the feasible solutions because we made it the feasible range on purpose, right? The only the solutions that are feasible would be generated. However, here we are actually still generating infeasible solutions, but the only thing is we're not traveling to them. So the neighborhood. So you remember how we generate neighbors for a particular solution. So in the algorithm operator, aka modifying the search space, we're not even generating neighbors that are infeasible. However, here we are generating neighbors that are infeasible. However, they will not be taken into account because they'll be too high. They'll be much, much worse than like what we're trying to do. Like what we're so if we're trying to, let's say, minimize, the neighbor solutions that are infeasible would have the penalty attached to them, which would make them a lot higher, and then we most likely would not take them into account. We won't travel to them. So that's the point basically. So it is better than not doing this because we can still remove constraints. So instead of having constraints listed as constraints, so this means that you generate infeasible solutions in the neighbors. So you generate infeasible neighbors. You'd move to those infeasible neighbors, and then you'd then realize once you're there that, oh shit, it's infeasible. You'd realize once you get there, right? So but here you don't even go there in the first place. You see the neighbor, it's clearly bad because it's had the penalty term attached, and therefore it's you don't go there in the first place. So it saves you a bit of computation, but not as much as the algorithm operators. However, the reason that this is used is because it's easier to implement and can be done in almost all cases. Whereas as we looked with the other ones, with the algorithm operator modifying, it can't be done in a lot of cases and it's a lot harder to do compared to this. So if you can modify the search space, if you can modify the algorithm operator, you always go with that I mean, if you can do it effectively rather than doing this, but this you can do a lot easier. So often you'll find that, yeah, you can do this easier. And that's my session pretty much. So the cons are, again, here's a little light bulb moment for you. If a strategy never enables infeasible solutions to be generated at all, then hill climbing and simulated annealing is complete. Meaning that this format of modifying the objective function does not necessarily make hill climbing and simulated annealing complete, because we're still generating infeasible solutions. We're just likely not traveling to them. You can imagine that we might still travel to them, especially if we used levels of infeasibility, and say we have a solution that's not very infeasible, but quite infeasible, sort of infeasible. Then uh, um, what's going on? Right. Which part are you talking about, basically? Okay, but let me just finish this for the recording real quick. So yeah, so with simulated annealing, hill climbing and sorry, with modifying the objective function, hill climbing and simulated annealing might not be complete, as we still generate infeasible solutions. But yeah, that's pretty much it for constraint handling and simulated annealing. Um, does anyone have any questions about the topic we've gone through? I'll look at the question you guys have just put in a sec. But for those of you that were there for the session, the entire session, um, can do you guys have any questions? I'll just finish the recording as well. Anyways, that's it for the recording, guys. Thanks for watching that simulated annealing and stuff.